Welcome to today's paper reading. Today's paper is titled, Agent Planning with World Knowledge Model. This paper, authored by Shuofei Qiao and colleagues from Jiang University and Alibaba Group, introduces a parametric world knowledge model, WKM, to enhance agent planning, particularly addressing issues of trial and error and hallucinatory actions in large language models. The work is currently under review. The abstract highlights recent advancements in using large language models, LLMs, as agent models for interactive planning tasks. Despite their success, these models still face challenges such as brainless trial and error in global planning and generating hallucinatory actions due to a poor understanding of the physical world. To address these issues, the authors introduce a parametric world knowledge model, WKM. This model allows the agent to self-synthesize knowledge from expert and sample trajectories, providing prior task knowledge for global planning and dynamic state knowledge for local planning. Experimental results on complex real-world datasets with state-of-the-art LLMs show that the proposed method outperforms various strong baselines. The WKM effectively reduces trial and error and hallucinatory actions, enhancing the agent's world understanding. Additionally, the model demonstrates better generalization to unseen tasks and can guide strong agent model planning, indicating promising potential for further development. Figure 1 contrasts traditional agent planning with planning enhanced by a world knowledge model, WKM. Traditional planning, as depicted in A, often results in trial and error and hallucinatory actions due to a lack of understanding of the real world. In contrast, B illustrates how WKM provides both global task knowledge and local state knowledge to guide the agent model, significantly reducing trial and error and hallucinatory actions. This approach mimics human cognitive processes, using prior knowledge to inform planning and maintaining dynamic state knowledge to adapt to changing conditions during task execution. The remarkable progress in large language models, LLMs, has significantly advanced various natural language processing tasks. However, when applied as agent models for physical world planning tasks, LLMs often generate actions that lack real-world understanding, leading to trial and error approaches. In contrast, humans use a mental knowledge model to rehearse tasks mentally before execution, incorporating global task knowledge and local state knowledge. This human approach inspired the development of a parametric world knowledge model, WKM, to enhance agent planning, integrating task and state knowledge from expert and explored trajectories. In this section, we introduce the partially observable Markov decision process, POMDP, framework used to model the interactive tasks. The POMDP is defined by the instruction space U, the state space S, the action space A, the observation space O, and the transition function T. The historical trajectory HT at time T is represented as a sequence of actions and observations. The policy model pi theta generates the next action at +1 based on the current trajectory HT. The world knowledge model, WKM, is introduced to enhance agent planning by incorporating both global and local knowledge, addressing issues in traditional agent models. Figure 2 provides an overview of our world knowledge model, WKM. The WKM is trained on knowledge synthesized by the agent model itself from both expert and explored trajectories. This knowledge serves two primary functions, providing prior task knowledge to guide global planning and offering dynamic state knowledge to assist local planning. The synthesis process involves comparing expert and sample trajectories to generate task knowledge, which is then used to train the WKM. This model aids in preventing blind trial and error and hallucinatory actions by integrating prior global knowledge and dynamic local knowledge into the agent's planning process. The method involves synthesizing task knowledge by comparing expert and sample trajectories. This process includes experienced agent exploration to improve the quality of rejected trajectories and self-knowledge synthesis. State knowledge is summarized based on historical behavior and stored in a state knowledge base to avoid confusion. The models are trained by integrating generated knowledge into expert trajectories and retraining the agent model with LoRa. At inference, the agent model plans with the aid of the world knowledge model, enhancing planning with global task knowledge and local state constraints. Table 1 presents the main results of various methods across different datasets. The best results are highlighted in bold, with the second best underlined. All prompt-based baselines are evaluated under one-shot prompting, while fine-tuning-based baselines are trained through LoRa. The red color indicates changes in WKM results relative to the optimal baselines. Notably, WKM demonstrates superior performance in ALF World and Web Shop, surpassing even GPT-4 in some cases. GPT-4 shows robust performance across multiple datasets, but WKM's ability to generalize to unseen tasks is particularly noteworthy. In this section, we discuss the datasets and metrics used for evaluation. We evaluate our method on 3 real-world simulated planning datasets: ALF World, Web Shop, and Science World. These datasets include unseen tasks to test the agent's generalization ability. The reward structures vary, with ALF World providing binary rewards and Web Shop and Science World offering dense rewards. We use average reward as the primary metric for evaluation. For models and baselines, we compare our method against state-of-the-art open-source models like Mistral 7b, Gemma 7b, and Llama 3-8b. We also include prompt-based baselines such as React and Reflection, and fine-tuning-based baselines like NAT and ETO. Additionally, we compare against ChatGPT and GPT-4. The training and inference setups involve fine-tuning with LoRa using the Llama Factory framework. Key hyperparameters include a learning rate of 1 × 10 to the power of -4, a sequence length of 2048, and training for 3 epochs with a batch size of 32. All experiments are conducted on 8 NVIDIA V132G GPUs within 12 hours. Table 2 presents the average number of steps required across different datasets. In ALF World, the maximum number of steps is 40, while in Web Shop it is 10. For Science World, the number of steps varies from 10 to 120 depending on the task type, with an average of approximately 40 steps. Table 3 presents the hallucinatory action rates on ALF World, detailing the proportion of trajectories containing invalid actions across different methods. Key points include the comparison of methods such as NAT, ETO, NoAgent, and WKM, and the performance differences between seen and unseen tasks. This table highlights the effectiveness of world knowledge models in reducing invalid actions and maintaining performance on unseen tasks. Figure 3 illustrates the ablation study conducted on the Mistral 7b agent model. The study examines the effects of different components of the WKM, world knowledge model, on the agent's performance. The without all condition represents the agent trained with only expert trajectories, while W/state and W/task denote the agent tested with only state knowledge constraints and guided by only task knowledge, respectively. The W/task and state condition is the WKM with both task knowledge guidance and state knowledge constraints. The results show that the WKM, especially with both task and state knowledge, significantly enhances the agent's performance, highlighting the importance of integrating world knowledge for effective agent planning. Table 4 presents the results of using a weak knowledge model, based on Mistral 7b, to guide strong agent models like ChatGPT and GPT-4. The findings indicate significant improvements in performance, suggesting that even a weak knowledge model can provide valuable insights that the strong models may lack. This approach, termed Weak Guide Strong, offers a new paradigm for agent learning, leveraging the flexibility of lightweight models to adapt to new environments without extensive fine-tuning. Figure 4 illustrates the performance comparison between human-designed dataset-level knowledge and WKM-generated instance-level knowledge. The results show that WKM's instance-level knowledge not only surpasses human-designed knowledge on seen tasks but also demonstrates superior performance on unseen tasks. This significant improvement highlights the strong generalization capability of WKM, which outperforms rigidly designed human knowledge. Figure 5 presents the relative performance of the multitask world knowledge model, WKM, in comparison to various baselines. The data reveals that the multitask WKM not only avoids performance degradation but also shows notable enhancements over the single-task WKM, particularly in the Web Shop and Science World environments. This observation aligns with previous studies that have successfully trained unified agent models, suggesting the potential of developing a unified world knowledge model that can assist various agent models and potentially generalize to guide new, unseen agent models. This raises the intriguing question of whether a combined unified agent model and unified world knowledge model could be the key to achieving artificial general intelligence, AGI. Figure 6 illustrates the performance of explicit state knowledge in agent planning. The results show that incorporating explicit state knowledge directly into the agent model significantly underperforms compared to the approach of retrieving state knowledge from a base and applying probabilistic constraints. In fact, the performance with explicit state knowledge is even worse than when only task knowledge is included. This highlights the inefficacy of extending prompts with extensive explicit natural language feedback for agent planning, suggesting that implicit knowledge constraints might be more effective. In the field of LLM agents, existing works primarily focus on agent planning, harnessing external tools, and code generation. These approaches often lack an intimate cognition of the environment, leading to trial-and-error methods and potential hallucinatory actions. Knowledge-augmented agent planning is crucial for intelligent agents, with some works utilizing pre-trained models and designing structured knowledge to regulate actions. However, these methods often require manual design and are challenging to transfer across different environments. LLM-based world models are common in reinforcement learning and robotics, with LLMs being proposed as powerful world models. In this paper, we aim to self-synthesize world knowledge to assist agent planning, differentiating our approach from traditional world models. In this study, the authors developed a parametric world knowledge model, WKM, to improve language agent model planning. The WKM successfully generated prior task knowledge for global planning and dynamic state knowledge for local planning. Results demonstrated superior performance on GPT-4 and state-of-the-art open-source models compared to various strong baselines. The WKM also reduced unnecessary trial and error and invalid actions, and showed better generalization to unseen tasks. Looking ahead, potential future work includes building a unified WKM, developing a world model for prediction, and applying the model to multimodal agent planning. However, the study has limitations such as the challenge of determining what a language model knows, the current text-only nature of the WKM, and the inability of the WKM to dynamically update with world changes and agent feedback. Thank you for watching.